Hello, everyone. Welcome to the Geology Department Summer Undergraduate Research Experience. I am Dr. Katie O'Sullivan.
And I'm Brianna Acevedo.
And together, we would like to introduce our research project, which is entitled Analyzing the Geochemical Composition and Mineral Characteristics of the Lunar Meteorite NWA 11788. And this meteorite research is really exciting. The meteorite itself is from the moon. It's composed of little bits of rocks and minerals that our students have been analyzing all summer long, looking at the chemistry, the texture, and the hidden pieces of information that are found in these really tiny little samples. And the sample is important for future research because
it can add to better constraints on the current model we have for lunar formation. The current model that we have is based solely on Apollo samples that were brought back from a localized region on the moon. So lunar meteorites can provide a more random sampling of the moon as a whole, which therefore can set better limits with our theories on the formation of the moon.
So with that, I will let the undergrad students take it away, and they will go into detail about each one of their miniature projects that they conducted this summer on this really interesting meteorite. Take it away, Brian.
Hello, everyone. My name is Brian Aguilar, and I'm going to be giving you a brief history on the background and methodology. The origin of the moon is a topic that is fervently debated due to the limited number of samples returned from the surface. It has been proposed that right after the moon formed, it existed as a lunar magma ocean, a vast world of flowing magma that reached unknown depths. Lunar meteorite NWA 11788 was analyzed more by using BSE and SEM imaging performed at UC Davis and UCLA. We compare the mineral composition of select class within our samples in order to understand the crystallization evolution of lunar meteorite. NWA 11788 thin sections were analyzed using a JEOL JXA 8200 electron microprobe at UCLA. Certain points of the class within thin sections were prioritized to determine if they harbor any unique characteristics. Using the results gathered from BSE, we are able to develop geochemical models, graphs, and interpretations in order to understand the presence of certain minerals associated with their evolutionary history. Okay, so now I'm going to be discussing the backscatter microprobe results. Each of these different images are of different class that were selected from the NWA 11788 sample. And so if we look at figure 1 to the left, we see fractures that are present on top and bottom of the observed class. The fractures could be what is responsible for what the offsetting that we see on the bottom portion. The lighter gray versus the darker gray represents the atomic number. So the lighter gray would represent a higher atomic number, and the darker would be a lower. And then those super bright spots that we see around to the left and the top are just metal oxides. If we look at figure 2, we see a pyroxene ground mass with plage crystals that are above. So the pyroxene would be the lower portion, and then the plage crystals would have grown on top. The ground mass radiates from the center. You could see it kind of makes like a wave-like pattern. There are multiple fractures throughout. The bright spots are the metal oxides. Size of the crystals tell us the cooling history, which was slow, and the pyroxene formed first, and then the plage second. If we look at figure 3, we see 2 different classes of varying composition. The top is mostly pyroxene. Again, we do see the atomic numbers. Again, the higher representing a higher atomic number of lighter color, and then a lower atomic number with the darker colors. Both classes contain plagioclase crystals. If we look at figure 4, we see the plagioclase class with olivine and pyroxene parallel to each other. There's offsetting that's occurring. We see that throughout, and tapering of the pyroxene crystal to the right portion. If we look at figure 5, we see a glassy deep texture of the pyroxene class. Has an intergranular matrix, and of course, there's metal oxides that are embedded within. There's also fractures that are present on both sides of the class, along with some vesicles that are within.
Hello, my name is Tabitha and I'll be discussing the pyroxene and its importance to my project. I focused on determining mineral composition of 17 different class within 2 slides, slides B and B9. Those are shown in figure 8 and figure 9 to the right. The class are just mineral fragments within a whole rock. So the focus was placed on a norite composition which consists of 50% plagioclase and 50% pyroxene. These are identified by looking at backscatter images as seen in figure 8 and figure 9. These images show felsic to mafic compositions as we can see on the scale. The plagioclase will show up as more felsic, is one of the more felsic minerals and shows up as opaque, while the pyroxene shows up as a medium to light gray, and these are both fragmented within our images. After identifying these classes as norite, I then compared the relationship between the magnesium and iron oxide and the magnesium to titanium oxide from our data to the data from the Lunar Mineral article, which looked at magnesium-rich rocks. The pyroxene is the most geochemically complex mineral, but also aids in recording and information on cooling processes and crystallization, as well as evolution history of lunar rocks. So I looked at the relationship of magnesium to iron oxides and magnesium to titanium oxides in pyroxene, and this just shows us how mafic composition is and records when crystallization happened. And mafic is just a term for dark minerals that contain ferromagnesium, and the mafic crystals present are olivine, plagioclase, and pyroxene. So after looking at these and identifying it as norite and focusing on the pyroxene aspect of this composition, we've seen that the pyroxene in our sample has a lower magnesium composition and a higher iron oxide composition, as we can see in figure 6. And what this tells us is that the magma is just less mafic due to less magnesium being present. In figure 7, we have the relationship between magnesium and titanium oxide, and we can see the differences between the different class. We have the paper analysis represented by a square marker, our B8 slide represented by circular markers, and triangles represent our B9 slide. So we see 2 groups. We have a higher titanium and a lower titanium group, and higher titanium just lets us know that the pyroxene crystallized before ilmenite, which is why it has more concentrated amount of titanium. Lower titanium lets us know that our pyroxene crystallized at the same time as ilmenite, which is why this titanium is lower. They're being shared amongst both of those minerals. And we see both of these types in our class. What this tells us overall is that the class came from 2 different types of magma that crystallized at different times, which is why we see these diverse lithologies. And I'll go ahead and pass it on to Diana.
Hello, I'm Diana Oregon, and I studied in the relationship between iron oxide, magnesium oxide, calcium oxide, and titanium oxide in class 6. First, I looked at the numbers individually, then I compared the magnesium with the iron and the titanium, and then I looked at the titanium, calcium, and the magnesium. Analyzing specific class can help identify the minerals present. Also, understanding the elements in each mineral can be indicative of how it was formed. The relationship between the oxides is important because it can give us an insight on the diversity of the class and overall in the meteorite. In previous research on the Apollo samples indicated that the low titanium oxide basalts have low magnesium oxide traces and higher iron traces. Therefore, the less iron in the basalt, more magnesium and titanium in the sample. The data gathered in class 6 in figure 10 follows the same trends as the Apollo samples. Although class 6 is considered a low titanium oxide, because the traces are less than 10%. The concentrations still follow the same trends and patterns as the Apollo samples. In this sample, there are 2 pyroxenes that were analyzed. In pyroxene 1, there is more magnesium and less calcium with a higher trace of titanium. In pyroxene 2, there's a higher concentration of calcium oxide compared to pyroxene 1. In pyroxene 2, since there is less magnesium oxide in the magma and also less titanium oxide in the concentration, is less than the first pyroxene. This data can indicate that the higher magnesium concentration, the higher titanium concentration will be in the magma, and less calcium oxides will be in the magma as well. In class 6, looking at the two pyroxenes indicate that these two came from different magmas, which means that the whole sample is diverse and is important to further research. Take it away, Connor.
Hello, my name is Connor Lesh, and I was tasked with studying the spinel in our lunar meteorite. The spinel in our lunar meteorite is a pink spinel class that is enriched in aluminum and depleted in chromium, titanium, and iron relative to ovospinel and chromite. The pink spinel in NWA 11788 contains low, less than 0.6 weight percent PaO2 and low, less than 15.08% FeO, or iron oxide. Because of this low amount of titanium, chromium, and iron, the pink spinel is classified as hercinite. Because it's classified as hercinite, this gives us a few options for formation theory. Pink spinel is commonly found in lunar troctolites alongside plagioclase and olivine, which are pink spinel, as you can see in figure 16, down at the bottom right, is also next to a plagioclase and olivine crystal. The figure 16 is a iron concentration map. So as you can see on the right side, you have a warm color, warmer being higher iron concentration. And this is representative of that olivine. And up in the top right, you see a very dark region or low iron concentration, which is plagioclase. As you can see, our pink spinel grain in the center there has some iron concentration, but not very high. That being because it is very high in aluminum. But you can see some higher iron around the rim of the spinel grain, indicating that likely iron was diffused into the spinel grain later on, post crystallization with all the aluminum. So one of the reasons or possibilities that all this aluminum was in the original melt could be because you have a magnesium oxide melt that interacted with anorthositic crust wall rock, and this allowed the magma to reach plagioclase saturation. So this may be responsible for the excess aluminum causing the formation or crystallization of a magnesium aluminum pink spinel. And this can be backed up by petrogenic models with greater than 50% normative anorthosite, because these models produced olivine, plagioclase, and spinel consistent with pink spinel troctolites. So our lunar meteorite, being a breccia, and could easily have pink spinel troctolites within it, classed within it, which contain these pink spinels. So future work should include comparing the NWA 11788 potential launch locations to regions mapped containing high concentrations of pink spinel. And we can move on to Jennifer.
Hi, my name is Jennifer Rubalcaba, and I will be focusing on the magnesium number in olivine and pyroxene. I'll start off by reiterating what clasts are. Clasts are small groups of mineral fragments within a larger whole rock, and the magnesium number percentages of olivines in class 1 were chosen to be further analyzed because there was a larger sample size of olivine crystals in that class than others for which the magnesium number was calculated. The magnesium numbers in class 1 olivine were further analyzed, and class 1 has a metamorphic texture seen in figure 17 to the right. It experienced higher temperatures, which allowed ions in the crystals to travel around to each other without the crystals melting. And this is why the olivine in class 1 has a much smaller range in its magnesium number as seen in figure 18 to the left, and therefore class 1 was metamorphosed. So what is the magnesium number? The magnesium number is a ratio of magnesium to the overall magnesium in iron sun, as seen in this calculation. So it's Ng over Mg plus Fe, and the percentage, you do that by multiplying by 100. And if the Mg number is closer to 0, then it's iron rich. And if it's closer to 1, it means it's magnesium rich. So the Mg number can tell us how primitive the magma is, and the higher the Mg number, the more primitive the magma is. The more primitive a rock, the more it resembles the original rock that it came from, and knowing more about the original rock can provide information on the lunar magma ocean processes. The magnesium numbers of pyroxene and olivine were analyzed and compared in this meteorite, and what was seen is that on average, olivine has a higher Mg number percentage than olivine as seen in figure 21. I'm going to take a moment to explain this figure. So this is a box in Whisker Plots, and inside the box, the line represents the median. The X is the mean. The top of the box is known as the third quartile, and it is the mean of the top half of the data. The bottom of the box is known as the first quartile, and it represents the median of the bottom half of the data. And then the top and bottom of the whiskers are the minimum and maximum, and below and above can be dots, and those represent outliers. And the outliers are calculated if they are further than the distance of the middle of the box from either the first or third quartile. So olivine has a smaller range of Mg number percentages as seen in both figures 19 and 21. And what this means is that the olivines crystallized over a shorter amount of time than the pyroxenes did. And pyroxene also has a wider range of magnesium numbers as seen in both figures 20 and 21. And what this means is that pyroxene crystallized over a longer period of time. So it witnessed more of the time from when the lunar magma ocean was magma to a solid state. Thank you. I will now be passing it on to Corelli.
Hi everyone, I'm Corelli Rodriguez, and my focus was on iron and magnesium composition in olivine and pyroxene. Olivine and pyroxene compose the first layer in the lunar magma ocean, as they are heavy minerals that are composed of dense cations like iron or magnesium. The composition of the minerals was examined to understand the trend when there are coexisting minerals that require the same cation. The data gathered on the meteorite was compared to the data in the published paper Lunar Minerals. All experimental data from olivine and pyroxene was used, while a subset of data was selected from the literature data that had the same label for both olivine and pyroxene. Looking at the figures, we can see that the shade of blue is denoted for iron, and then magnesium is denoted in orange. Figure 22 shows the comparison of iron and magnesium composition in olivine between the experimental and literature values. It shows that there was a greater variation in the literature data for both iron and magnesium, while the experimental data had a lower variation. Looking at that graph, we can see that there's a positive distribution for iron overall and a negative distribution of magnesium. We can see that as we can look at the X denoted in the box plot, which stands for the average value. Looking at figure 23, we can see a comparison of iron and magnesium in pyroxene between the experimental and the literature values. Just like figure 22, we can see that there's an overall positive distribution for iron, while there's a negative distribution for magnesium. In figure 23, we can see that there is a greater variation in the literature data for iron and magnesium. And there is a there's a low variation of both the iron and magnesium values in the experimental. To conclude our research, we can see that there was different textures of sample Northwest Africa 11788 that indicate varying degrees of pyroxene ground masses along with co-crystallization of plagioclase crystals based on BSC imaging. There were high and low abundances of elements, signifying two types of magma. Pink spinel in Northwest Africa 11788 is aluminum rich, plotting it as hersenite. Aluminum rich spinel spinel likely formed through magma wall rock interactions with anorthosite crust. Pyroxene had a large range of magnesium number percentage than olivine, signifying pyroxene crystallized over a longer period of time than olivine. Then there was a higher composition of iron than magnesium in pyroxene and olivine for both the experimental and the literature data. Lastly, we would like to express a special thanks to Chevron and Title 5B Graduate Excellence Program for funding the SURE program at CSUB that allowed us all this golden opportunity to conduct research. Secondly, we would like to thank Dr. Katie O'Sullivan and Brianna Acevedo for guiding us all, and thank you.